Previously, we discussed concepts like replication, sharding techniques in the distributed systems. These techniques solve important database level problems. For example, replication improves fault tolerance and availability by copying the same data across multiple same machines, and sharding, on the other hand, improves the scalability. Instead of storing all data on the one server, data is partitioned across multiple machines. This reduces storage pressure and the distributed query load. However, replication and sharding mainly solve storage and the database access problems. They can help us store more data and serve queries and reliability, but they do not automatically solve large-scale computations. For example, imagine we are building Facebook or the Instagram network platforms. Every second, millions of the users are uploading the photos and the videos, liking posts, sending some kind of messages, and so on. Even if all data is already sharded across many database servers, the company still, for example, the demanding the platform's request still needs to perform large-scale computations, especially like generating personalized, for example, recommendations, or detecting some kind of the trending content for the statistics like this. So these tasks require processing data from many servers together. A single DB query is not enough. So the challenge is no longer only where the data is stored, but also how to compute over massive distributed data efficiently. This is a main difference between distributed systems and the distributed computing. This is where we can distributed computing and some frameworks become essential. So distributed computing is model where multiple independent computers are networked together or common tasks. Only adding memory or just the CPU is not optimal because they have principal and financial limits. For applied distributed computing, we can use some kind of big frameworks. One of these, MapReduces. These type of computation techniques are to process huge amounts of the data in parallel across many machines. So we can see in here MapReduce's fully architecture and its workflow system. Let's imagine we have some kind of inputs and its the steps. Firstly, we need to know the MapReduce's meaning. MapReduce has two main phases, which are map, task as an input chunk of the data from the file, process it, and gaze as an output sequence of the key and value pairs. And reduce part is task as an input and the key, all values associated with that key, and produces output which is stored. This is two main parts of the MapReduce architecture. So if we can say in here, if we input some kind of, for example, this input texts, for example, in here some kind of words are the similar, and after the input, the next process, it splits all of the data as a input size. For example, in here the layers, for example, first, second, and third layer, this is a splitting process. It splits into chunks. We call it chunks. Each chunk can be processed independently, like these independent layers, and it enables, why we need, because it enables parallel processing. That's why we need to split them. So the next process is we call it shuffling, which is, for example, beer, like this word, how many, for example, times it partition it, like beer 1 and 2. This is the shuffling process. We can divide and we can collect them one, for example, layer. The second word, for example, the car as well, 1, 2, and 3. We can shuffle it like this, one layer. So why we need this shuffling? Because each chunk is processed separately, as we said, and this is for example local transformation, like the collection version. So, and it groups the same keys together. That's why we can, as we said, key and value parts. This is a key part of that process. It usually store like this version, for example, beer, partition it 1 and 1, for example, this is a key and value. The car, 1 and 1 and 1, for example, again. And after that, reducing parts works, like for example, beer 1, 1, and full total partitioning is becomes, for example, 2, and like this, and other inputs also collecting for the output final result. And we can see in the final result like this version. This is just a simple version of the MapReduce's architecture. So let's example. Imagine we have a big system like for example Google search engine or Chrome for the Google. There are billions of the web pages on that platform. When users, like for example, search some kind of words, for example, what else? Replica. User sent the request, for example, like these words, and we have a big, huge amount of the data. It needs to respond like these words that partition it how many times or how many pages or how many, for example, the articles. We partition it. We need to find this word, for example, this input. So our solution is like this workflow replication sent to in here as an output. It split it, shuffle it, reduce it, and give the final result. So in conclusion, the MapReduce to pre-build an index of the all pages that tell us what word is where. You put or some kind of, for example, the query is where. This is a main solution, and this is the main concept of the MapReduce's simple architecture form. So the next concept is HDFS. So every MapReduce job needs distributed file system to store input data and output data results. This process works with Hadoop distributed file system. Hadoop distributed file system. What is it? HDFS is a highly fault-tolerant, open-source distributed storage system designed to manage massive datasets, like not only just a megabyte or gigabyte, but gigabyte, terabyte, and petabyte data across clusters of the commodity hardware. Like it is a primary storage component of the, for example, Apache Hadoop. We'll discuss about that. Optimized for high throughput batch processing rather than interactive use. And its architecture is uses master-slave architecture consisting of the name nodes and master nodes. We can see in here its architecture. Like we have a one manage data, metadata, and data nodes store actual data blocks. Its main purpose is fault tolerance, like files are replicated across multiple nodes, and ensuring data availability even if the hardware fails, like the sharding version. And its scalability part is designed to scale horizontally, adding more nodes to cluster increases both storage capacity and the throughput. And this part means name node is manage the file system namespaces, like for example directories or files, and regulates client access. If the client requests some kind of request, firstly master node receive it, and then distribute to another slave nodes. And it stores metadata including file permissions in the memory. And data node is, like we can call it slave nodes also. It stores the actual data in the files. Typically, for example, creating 128 megabytes, or for example 256 megabyte blocks that perform block creation, like deletion or duplication, upon instructions from the name nodes. So Hadoop is the best for, as we said, huge datasets like terabytes and petabyte datas, and fault-tolerant storage systems. And its advantages are, it is a horizontal scalability, and we can add more machines like this, and it can handle the large data sets, and it's cost effective. This is the main advantages of the Hadoop file system. And its little bit drawbacks we have some. Firstly, it's slow. It means it usually requests directly to the disk. Input output, and of course it's not a real-time application. And also we have the main structure, inside structure of the Spark, which is a RDD. RDD is a core data structure of the Spark, of course, and it is immutable, distributed collection of the data partitioned across multiple nodes. It works for this process. So RDD means like resilient, D means distributed, and another D is dataset. It works with the data part. So resilient means if some node fails, Spark can recompute lost the data like by replying and recorded like lineage. That means history of the transformations and produce it. No data is permanently lost. And distributed means that data is automatically partitioned across many machines in the cluster, and it enabling the parallel computation. So another D is a dataset. This is a collection of the data, of course, and it could be lines in a files, like database rows, JSON records, or any kind of structured or unstructured data. So RDD supports two main categories of operations in Apache Spark. Firstly, transformations and actions. Transformation means like it creates a new RDD from the existing, but do not trigger computation immediately, like map and reduce. An action means trigger actual execution and the return result write output, like examples with, for example, collect or count or some kind of reduce. These mainly functions. So these approaches allow Spark to optimize entirely computation and improve performances.